Hello everyone. Today we're going to learn about two-pointers algorithm. As the name suggests, with two-pointer we're going to have access to two data points at a time. That's one more data point, 100% more compared to for loop or any other previous method. Having access of two data points at a time with two pointers is going to be useful in many cases, and it's going to bring down the time complexity of the algorithm. This tutorial is a part of the Data Structures and Algorithms class. First, we're gonna have a look at a typical problem solved by two-pointers algorithm. But before that, we're gonna briefly talk about two-pointers and how it works. Two-pointers give us access to two data points at a time, and one pointer at a time we move toward to the other pointer. It's also important to know that our solution is only correct if the logic of moving the pointers will not miss any meaningful data points. And we're gonna know more about this statement later in the examples. A quick comparison of for loop binary search and two pointers. For loop and binary search, we only have access to one data point at a time. With two pointer, we can access two data points at a time. That is 100% more. Time complexity for loop is O(n), binary search is O log n, and two pointer is O(n). But for two pointer, this O of n time complexity gives us access to two data points at a time. So if we need to do the same thing with for loop, that's gonna be two nested for loop, and that's gonna be O(n) square time complexity. So you can see if we can use two pointers to access two data points at a time and solve our problem, we can already bring the time complexity from O(n) square to O(n), and that is a great reduction of time complexity. For special requirement to use binary search, we must sort the array. For two pointer, sometimes we need to sort it, sometimes we don't. It's really depends on the logic of moving the pointers. Now let's have a look at a typical problem solved by two-pointers algorithm. And our problem is, we are given an array of numbers and we are asked to find three numbers that's gonna add up to a given sum. So basically we're gonna pick three numbers from this array, and those three numbers need to add up to a sum of 30. To solve this problem, by now you should have at least two straightforward methods that you have learned so far, and we're gonna briefly mention them here. The first one is brute force. We're gonna list all possible subsets of 3 and pick the set that sum up to the target. So that's gonna be 3 nested for loop. And the time complexity of this method is O(n) power 3. This is the easiest way with the higher time complexity of O(n) to the power of 3. Next, we have a more efficient method. Because we see that brute force is O(n) 3, we immediately think about sorting and binary search. So we sort the array, that's gonna take O(n) log n. And we're gonna use two loops to pick the first two numbers, and then we're gonna use a binary search to find the third one. So that's gonna give us O(n) square log n time complexity. This is better than O(n) to the power of 3. But the question is, can we do better? And two pointers say yes. In this case, we're gonna sort the array, and what we're gonna do is we're gonna start a for loop to pick the first number, and we're gonna use two pointers to pick two numbers, and the pointer begin at the leftmost and the rightmost positions. And then we're gonna move our pointers one at a time toward the other pointer. So for step 1, with for loop, we already picked 2, and with the left and right pointer, we picked 3 and 26. That's gonna add up to 29, but our target sum is 30. So our current sum is bigger than our target, and we're gonna use this information to move the pointer. Because this is a sorted array, we know that the number is increasing from left to right. So if the sum by the two pointers bigger than the target sum, we will move the right pointer to the left. That means we're gonna move from 26 to 22. Because we know if we go to this direction, the sum of the two pointers will decrease. And that's what we want. We want the sum of the two pointers to meet the target sum. For step 2, we're gonna recalculate the sum and compare it to the target sum of 30. This time we have 2 picked by the for loop, then we have 3 and 22 picked by the two pointers. So that's gonna give us 2 plus 25, and we know that it's smaller than the target sum, which is 2 and 28. In this case, we're gonna move the left pointer to the right. So if we move the left pointer to the right, we know that the sum of the two pointers is gonna increase, and we want it to increase and match 28. For step 3, after moving left pointer from 3 to 5, we're gonna recalculate the current sum. That's gonna be 2 plus 5 and 22, gonna give it 27. And 27 is still smaller than 28. So we're gonna move the left pointer to the right. And if we keep doing this, the 2 pointers gonna converge at 13 and 15. And that's gonna give us the first set of 3. 2, 13, and 15. That's gonna sum up to 30. That is how 2 pointers works. Now, you might have noticed that by moving the pointers like this, we're missing out some possible subset of 3 compared to brute force solutions. For example, in this case, by our first 3 steps, we have missed the combination of 2, 5, and 26. But because this array is sorted, we know for sure that 2, 5, and 26 is an unmeaningful subset. Why? Because the subset before it is 2, 3, and 26. And we know that 2, 3, 26 is already bigger than 30. And because this array is sorted, the next number after 3 is gonna be bigger than 3, which is 5. So we know for sure that replacing 3 with 5, the sum of the 3 numbers is gonna be still bigger than our target. And that's why we're not visiting it. And a 2 pointers setup will not visit unmeaningful subset like this. And that's why 2 pointers is more performant than our 2 previous methods. In our case here, the time complexity for 2 pointers is gonna be O(n) squared. That is much better than O(n) squared log n, and of course well better than O(n) to the power of 3. Next, we're gonna have a look at the implementation of our 3 methods. The first implementation is brute force. We're gonna use 3 for loops. The first one to pick up the first number, the second for loop to pick up the second number, and the third one to pick up the third number. If the 3 numbers sum up to the target sum, we're gonna save it to the result. And we're gonna return the result. And if we run this, it's gonna give us 15, 13, 2, which sum up to 30, and 3, 5, 22. So we have 2 sets of 3 numbers that their sum add up to 30. And because we have 3 nested for loop, our time complexity is gonna be O(n) to the power of 3. Next, we're gonna have a look at the binary search implementation. First, we sort the array. That's gonna take O(n) log n. Then we use 2 nested for loop to pick up the first number and the second number. Then we're gonna use the binary search to see if we can find the remaining number. And if we do, we save it to the result array. And if we run this, this is our result. We have 2, 13, 15, which gonna sum up to 30. And we have 3, 5, 22, also sum up to 30. And we can see that both methods produce the same result. And because this is 2 for loops with 1 binary search, our time complexity is gonna be O(n) squared log n. Lastly, we're gonna have a look at our 2 pointers implementation. And it's surprisingly a simple implementation. First, we sort the array. That's gonna take O(n) log n. Then we use 1 for loop to pick the first number. And this is our 2 pointer implementation. We initialize the leftmost pointer and the rightmost pointer. And we're gonna loop while left is still smaller than right. We pick the second and the third numbers with our 2 pointers. So our current sum gonna be the sum of 3 numbers, the first number picked by the for loop, and the second and third number picked by the 2 pointers. If the current sum equal to the target sum, we find a possible set. And we're gonna save it to the result array, and we break out the loop. If the current sum is bigger than the target, we want to reduce the current sum, so we move the right pointer to the left. Or if the current sum is smaller than the target, we want to increase the current sum, so we move the left pointer to the right. And after we finished, we return the result array. And if we run this, it's gonna give us the same result with the 2 previous algorithms. We have 2, 13, 15, and 3, 5, 22, both all sum up to 30, but with a much better time complexity of O(n) squared. Next, we're gonna generalize the characteristic problems that can be solved by the 2 pointers algorithm. As you can see a few seconds ago, using and implementing 2 pointers is very simple. It is even simpler than binary search. So the way that you can use 2 pointer is, you can quickly try and see if it solves your problem, because it doesn't cost us much time to try. Okay, so the characteristics of problems that can be solved by 2 pointers is that for your problem, accessing 2 data points at a time is useful. And when you use it, with the inputs you have to make sure that closing in the pointers, meaning moving them toward each other, proven to give a correct answer. That means it's proven that you're not gonna miss any meaningful data point. And the input type that you usually have is string or array. So if these things checked, you can use 2 pointers algorithm to have a good time complexity of O(n). Let's have a look at another example, and this is called container with most water. We are given an array of heights. The numbers in the array represent the height of a wall. For example, the first height is 1, then this wall height is 1, the second one is 8, so this wall's height is 8, and so on. And these walls is distant by each other by 1. So you can think of these numbers are indexes of the numbers in this array, but the index starts at 1 instead of 0. Now if we have two walls, it's going to create a container that can keep water. For example, the first wall of 1 and the second wall of 8. We're going to create a container that can keep like 1 unit of water because the height is 1 and the length is 1. Water level cannot go higher than 1 with these two walls because the height of the walls in the left side is just 1. And the question for our problem is, given the wall's height like this, what is the most water that we can have? Now we're gonna apply what we learned about two pointers to solve this problem. We can obviously see that accessing two data points at a time is useful in this case, because we need two walls, two heights, and that's two data points. Now we try to see if closing in the pointers proven to give a correct answer. For step 1, we start the pointers at the leftmost and rightmost positions, and we got 1 and 7. The distance between 1 and 7 is gonna be 8. That is 9 minus 1. We're gonna need the height to multiply it with the distance to get the water area that we have for these two walls. So we have the heights of 1 and 7. And of course we have to take the lower height. And the water area between these two walls is gonna be this blue shade here. So that 1 multiplied with 8, it's gonna give us 8. Now we need to move a pointer. And because 1 is smaller than 7, we're gonna move 1, which is a pointer on the left. We want to keep the bigger height, which is 7 in this case. And this logic, by replacing the smaller height, we are sure that we're not gonna miss the bigger heights. So in step 2, we move the left pointer to the right. Now it's at 8, which is this wall right here. Now we have the wall of 8 and 7, and the distance between these two walls is 9 minus 2. That's gonna give us 7, and we have to take the smaller number between these heights, which is 7, to multiply with the distance, which is 7. That's gonna give us the water area in pink right here, and that's gonna be 49. And for the next step, we're gonna move away from 7 because we want to keep 8. So for step 3, we're gonna move the right pointer to the left, and that's gonna bring a 3. So the new height is gonna be 8 and 3, which is these two walls here, and the distance gonna be 8 minus 2, which is 6. And the water area in the orange gonna be 3 multiplied with 6, gonna give us 18. And we're gonna keep doing this while the left pointer is smaller than the right pointer. And after we finished, we have 49 as our most water area. But let's have a step back and have a look at a set of walls that we have not visited after these 3 steps. That is the wall 1 and 3. As we can see here 1 and 3. We did not visit 1 and 3. And the previous set we visited is 1 and 7. When we were at 1 and 7, we chose to move away from smaller height, which is 1, and in fact is a logical good choice, because 1 and 3 is unmeaningful to visit. It's nothing better than 1 and 7. So in our particular case here, with this logic, we are also skipping unmeaningful sets. Next, let's have a look at our implementation for finding the container with the most water. We're gonna go straight to two pointers algorithm. We have the leftmost pointer, we have the rightmost pointer, and we initialize the most water as 0. Then we're gonna loop while the left pointer is smaller than the right pointer. We recalculate the new water area. Every time the pointer moves, we compare the new and the current water area and keep the bigger one. We print out some information. Here's the logic to move the pointers. If the wall on the left is higher, we move the right pointer. If not, we move the left pointer. Then we return our max. And if we run this is our result. And the most water area we have is 49. Next, we're gonna summarize our two pointers algorithm. We can try to use two pointer with any problem. As long as when we look at the inputs, accessing two data points at a time is useful. And we can prove that closing in the pointer can give a correct answer without dropping any meaningful data points. And the input are usually array or string. Then two pointer algorithm gonna give us a good time complexity of O(n). That is all for today's tutorial. Thank you for watching, and I will see you in the next video.